if you allow science to go the way where it wants to go, that you can go to very unexpected places. But I mean, you have to be a little bit brave for doing that. And you're going to see this in this talk, how totally surprising things have happened in the way where I've been going. So there's a lot of sort of historical forward and backward going here. Okay, so like what the slide is saying is like, how do you get from like childish pictures to actually something very practical and applied? You'll see how that works. So, okay, so just to repeat, so I used to be a professor at Oxford University for very long. I left, but before that, I built a very big group, the quantum group, and a lot of people actually left with me. So a lot of people, basically everywhere in foundations, went at some point in their life through this group. So I'm not at Oxford anymore. So I became chief scientist at first Cambridge Quantum after a while. And then the name suddenly changed because we actually merged with Honeywell Quantum Solutions. Honeywell Quantum Solutions was the part of Honeywell that actually builds quantum computers. And so together we're now Quantinuum. So I've got a team. I've got a team in Oxford under Quantinuum. So I'm chief scientist globally. We're a company with about close to 500 people now. So I built my own team in Oxford in quite a short time. People will recognize many faces there because they're members from the community. Well-known members from the community. This is our logo. So everybody has a t-shirt like this, like me. This is our basement. Was paid for by the company. And both my old group and we as Quantinuum are actually part from the QISS consortium, which is with which this talk is associated and which was described in the introduction. So we're now two parties. Okay, let me start with a talk. I'm going to talk about the language of quantum. The language of quantum. So I'm going to do this by means of some important figures. So this is John von Neumann. So some people may know him from game theory, which is now very important in economy. Whatever computer you have in your hand, it's a John von Neumann computer. That's the architecture which actually every computer now has, every classical computer. And he's also one of the most important mathematicians of the previous century. I would say at least one of the two most important. But then something else he did, John von Neumann, is that he actually also proposed the formalism of quantum mechanics. This is the language which scientists use to do quantum mechanics. And he came up with that the book came out in around 1932. And so it's still the thing which, if you go to university, that people teach you. It's still the same thing that people teach you at university. It's the same language. But a really funny historical fact is that already in 1935, the book was published in 1932, von Neumann himself denounced that language for quantum, which we are still using today. And an important, like I said, he was a very important mathematician in the previous century. A lot of the mathematics he developed was actually with the goal of coming up with a better language for quantum. A lot of what he did was with that goal, but in the end, he kind of failed. He came up with things, but none of these things are now really used in any important way. Okay, so that's a little bit of history. Here is somebody else. This is Erwin Schrödinger. You may know him from his cat, or you may know him from his equation. But another thing Schrödinger said, the same year as von Neumann denounced the quantum formalism, the same year, Schrödinger so let me make a context. So what von Neumann said was that in order to come up with a new language for quantum, we should think very hard what happens if we take a quantum particle and we look at it. That's what we should focus on. He says that what happens then, we disturb that particle, it changes just by observing, and that's what we really should focus on to come up with a new language for quantum. This is like the most important ingredient of quantum. That was von Neumann's story. Schrödinger said, no. The most important thing of quantum is what happens if you bring two things together. I've got two things. I've got sort of my box of glasses and my glasses. What happens if I bring them together? Well, this is still a box of glasses and this is still a pair of glasses. Now in quantum, this is a little bit different. If you bring two things together, stuff happens between them. there is some sort of form of togetherness which is created and which has no counterpart for glasses and for glasses boxes. For the things in our world, there's no counterpart. And that's what von Neumann said is the thing we should really focus on. So what happens when we bring two things together? Sort of structure of togetherness, or in another word, the structure of how things interact with each other, the way how things interact with each other. So that was von Neumann's story. Okay, this is another person. Unlike the previous two, he's still alive. That's Roger Penrose. He got a Nobel Prize recently. He's also based in Oxford, by the way, in mathematics. You may know him from like Euler's paintings, because actually, say the name, not Euler, Escher's painting, because actually they were close friends, and Penrose actually gave the inspiration to Escher for these paintings. Or you may know him from the black holes, which gave him the Nobel Prize. But then another thing Penrose did was, and this goes back, this is in a paper in the early 70s, and this goes back to the late 60s, when Penrose was an undergraduate student. He actually really hated this sort of math symbols. This is what people use in relativity theory. He hated them. He thought they were just horrible to work with. And he replaced them by pictures. So for different kind of things, he came up with different pictures. And so he came up with a picture language specifically for some mathematical symbols he actually didn't want to work with. So that's the thing Penrose did. Right. And I wrote a paper in 2005. And this was mainly trying to realize Schrödinger's view from Penrose's pictures. Now, these are all very smart people I showed, like two Nobel Prizes and one who doesn't have a Nobel Prize because there happens to be no Nobel Prize for mathematics. That's the only reason. So these are neat. And so I'm gonna actually use kindergarten stuff to solve a problem they had or to realize a thing which they have. Well, this was just a plan. This was just a plan. And the fact that this was kindergarten quantum mechanics is just a lie. This was not kindergarten quantum mechanics. This was just a way to attract attention. That's why I called it like that. But there we laid out a certain plan. And the plan was, can we use pictures like Penrose's one to do all of quantum mechanics? Because I understood at the time that these pictures were really the way to focus on togetherness, to focus on interaction of systems, to actually start a new kind of description of quantum mechanics, which really took like this view that the most important thing and the only thing you really need to count for is what happens if you bring things together. So that was the plan. And so there were a few pictures inside. I'm not going to explain them. In the paper, you find pictures like that. I'll explain the same picture later. Anyway, that was the plan. 13 years later, we brought out this book, me, myself, and Alex Kissinger, who's a former PhD student of me, and now pretty much has taken over the group at Oxford, which I built. So we brought this book out in 2017, and this was the realization of what I wanted to do. This includes a full course of quantum theory and quantum computing entirely expressed in pictures, just pictures. There's no sums, there is no typical math, calculus symbols, it's just pictures. And it's very thick because we actually also explain how you should do it, and we explain how it relates to the usual stuff. And it's definitely not kindergarten. It's definitely not kindergarten. I think you better be at university to start reading it. It's a little bit difficult still. It took us 3 years to write and 5,000 or 6,000 pictures to draw. Well, actually, it's 20,000 pictures because you throw a lot away. But anyway. And if like me, you've got OCD, it's a serious problem. Anyway, so just to give you an idea of the sort of so how do pictures comprise mathematics? Pictures comprise mathematics by basically making all the kind of calculations you want to do implicit in the sort of connectedness of things. Like, for example, here you see a piece of wire. I could take any piece of wire here. I don't want to disturb whatever is going on here. I don't think that has anything to do with it. But if I have a piece of wire and I hang it like this, or I hang it like this, it's just the same thing. It's not going to change anything. So that's the kind of equations you use. And this is basically what explains quantum teleportation. Like quantum teleportation, which I will later explain, a very important thing in quantum computing. It really completely follows from this one equation. Another thing, which is, for example, suppose I'm doing the same thing and there happens to be like some sort of bead on the wire. There happens to be some sort of bead on the wire. And you pull the wire, then it's going to rotate. It's going to rotate 180 degrees. This happens to be a very important concept in linear algebra, which like in the mathematics of quantum mechanics, and for those people who know a little bit of linear algebra, this is the transpose. This is the concept of the transpose, just rotating something. That's what the transpose does. And then you have to do a lot more. Then you have to do a lot more, of course, to get to full-blown quantum mechanics. This is the beginning. 5 years later, okay, finally, we're getting there. So this is a new book, which is not out. It's going to come out in September. The surname of my co-author is misspelled because this is not the final cover. Yeah, this is sort of the design. And this is intended for we don't know which age, because we have to do experiment to figure it out. But we've had like children from even 13, 14 years read it, and they get it. They get everything what's inside. So this is really now going down to a much younger age to teach. Basically, this book includes things which we didn't know yet in the big book. So it has cutting edge bits of new quantum computing in it, which were not in the previous book. And since this is a public talk, so this is going to come out. We're going to bring this out in 2 versions. One really cheap, one really cheap that everybody can buy. And one really expensive and fancy for people who don't read it, but just want to show up with it. So those are going to be the 2 versions. The other version doesn't look like that. It's looking more like an art book or something like that. Anyway, so this is my office. This is my office, my new office. And so this has been turned into a film studio because we've filmed the entire book, like presenting with a lot of silly jokes and with a lot of like cameos of like von Neumann and Einstein and other people. And so this will also be made available maybe earlier than September, maybe like somewhere in the summer, because we're basically done. Okay, so I'm now going to sort of rush you to 2 chapters of this book. This is really, I mean, these chapters are like 20 pages. I'm just going to do it in now 1 or 2 minutes each. So of course, this is speeded up, but you will get the gist of things. So the ideas in there is that these pictures represent things like boxes, like devices, like a lamp. Maybe we'll have boxes in there, like this battery and this lamp, and we will have wires in there. And the idea is boxes is where you may produce particles, or you may use particles, or you may change particles, and wires is like where the particles travel from one box to another. That's sort of the intuition between this language, for this language. And then we're not going to always make the effort to draw a lamp or a battery. So this is a wire, and this is a box. This is a box, and a box can have some wires coming in, and a box can have some wires coming out. Like you can plug something in your phone, or you can plug something anywhere. It's kind of the same idea. So this could be water coming in whatever, in a heater, and then hot water coming out, or something like that. So this is wires and boxes. Okay, and then you can actually plug all that stuff together. You can plug all that stuff together in what, well, we call a diagram, but it doesn't matter. Call it whatever you want. It's, yeah, whatever. It's not important. We call it what the name is. But things get really important and interesting. So I'm now going very fast. I'm going very fast. When you remember my piece of wire like that, and I said, yeah, you can just yank it and then you get the same thing. If we now want to think on this little cup-shaped piece of wire and this little cap-shaped piece of wire as boxes themselves, so we can just draw a box around it, and it's a box here with 2 wires coming out, and here is a box with 2 wires coming in. So we can just stick it in a box, and it becomes a box itself. If you do that, then things become really interesting. As I will show now. For example, it's sort of, so here we can basically slide other boxes around this box if we want to. We can slide other boxes around this box. So it's sort of boxes passing through each other, and this box changes. You see, this box is 180-degree rotation of this box. So that's one interesting thing it does. I said that's how you create the transpose. Now let's go to something more out there in space. So this is a very badly drawn galaxy. This is from the previous draft of the book, because the publisher said that it's too ugly. And so now we're actually drawing some planets because they look a little bit nicer, because this galaxy picture was so ugly. Anyway, the way to think about this picture now in terms of space and time is that whatever's at the bottom of the picture is very early, is in the past. Whatever is in the top of the picture is maybe now. So whatever is here is in the past, this is now, and now we got Andrea on one side of the galaxy, we got Blaise on the other side of the galaxy. Here you see this cup-shaped wire, which you can think of as a box. And basically this is two particles come out of the box. One particle goes to Andrea, the other particle goes to Blaise, and then Andrea does something to it and Blaise does something to it. Does that make sense? That makes sense? Very easy to understand. Well, maybe not that easy, but so something here is produced by this box, goes to one particle goes to one side, the other particle goes to the other side, and they do something. And that's, I mean, this particular picture is very, very, very important. In the conference today, we had very professional scientists, and a lot of them drew that picture, by the way. I can tell you that. So it's a very important one. People have been thinking about that picture for some 50, 60 years, and they're still arguing about it, what it means. This one picture. Anyway, I want to show you this picture because that's much more clear cut. So what I do now is I start in the same way. I send a particle to one side of the galaxy, particle to the other side of the galaxy. And here at Andrea's side, there is a box, another particle, say, which is produced by a box. And then what Andrea does is she uses this other kind of weird box, this cap box. So this is the picture we have now. We can just take this one and slide it along this whole wire to the other side. So basically, what this is showing is that after sliding, whatever was on Andrea's side is at Blaise's side. And this is like a very important phenomenon people call quantum teleportation. The fact that you can use these cups and these caps to get something from one party to another party. That's kind of quantum teleportation. And of course, with these wires and boxes, it's an obvious thing that you can do that. But you should realize that the professionals who studied very hard von Neumann's quantum language, they needed 60 years to come up with this. 60 years, 60, to come up with this. And these were very smart people. There were a lot of very smart people involved. So these pictures make discovering quantum teleportation very easy. That was the main thing I had in 2004 and 2005, really. Okay, now we go. So this was one chapter. Of course, in the book, it's much longer and much better explained than I'm doing now. But anyway, so now we go to the second chapter. And that's more interesting. That's about spiders. Spiders are funny creatures. So what is a wire? What is a wire? Okay, it's good. Okay, here's a wire. These are actually two wires not together, but think of this as a wire. So what is a wire? Okay, I got one endpoint, which is this thing I stick in my phone, and I got this other endpoint, which is the thing I stick in my ears. But actually, these are two wires, because these are a little piece of wire. So this also has one endpoint and one endpoint. And this also has one endpoint and one endpoint. And now I stick one endpoint in the other endpoint, and I still get one wire. So a wire is a thing that if you connect it with another wire, still get a wire. So you don't get many wires out of wires. Okay, so that's a wire. Now, that's what I just explained. If you glue two wires together, you get another wire. And that's a spider. And the idea of a spider is a wire with more than two ends. A wire with more, and okay, and it's also more cute. It's cute, huh? It's cute, huh? So but you have to think of it as a wire with more than two ends, or less. It can be one, or it can be zero even. It can be zero even. But that's cruel. That's cruel. Any spider with something else than 8 legs, that's not nice. That's cruel. Although some of them have more than 8. That's scary. Anyway, so what I said, what we had with wires, if you glue two wires together, you get again a wire. if two spiders meet each other, you get again a spider. That's how it works. You have to do a little bit of counting now so that the number of legs here and the number of legs there is the same there. But that's the idea. So they fuse together. Spiders fuse together. So it's the idea of a wire with multiple legs. And what is a really funny thing is, you remember our previous type of you take a wire with a band, you yank it, you get another wire. You see, here we got a spider, we fuse them together, and we get a wire. It's the same, it sort of shows it's really a generalization of this idea of having wires. Okay, let's go on. Right, okay. Now, the animal world would be very boring if there would only be one kind of animal, right? So we got two kinds of spiders. But as you can imagine, they don't like each other. They don't like each other. So when we've got the green spiders, we got the red spiders, and when they meet each other, they hit each other and then their legs fall off. They sort of, one does this, the other one does that, and boom, their arms fall off. Because yeah, the spiders are not supposed to punch each other. So you see, whenever there's two wires between a green and a red spider, it falls off. That's the rule for the color spiders. Now, we can start doing quantum computing with these spiders. Quantum computing is now becoming very, very big. It's becoming a big industry, and it's about building new kinds of computers which can do all kinds of things which our normal computers can't do. So it's studied a lot, and these spiders can be used to study quantum computing. So what you see here is something that could be sitting inside a quantum computer. So basically, you have to think of this as quantum particles, these lines as quantum particles, these lines as quantum particle, this line as quantum particles. So we got three quantum particles. Like in a computer, you would have three, what people call bits. So you got three quantum particles. And then you have to think of the red and the green spider next to each other together as one box. Think of them as one box. So we got three boxes here. We got that box, we got that box, and we got that box. And this is a thing which has a name. People call this, professionals call this a C0, or engineers call this a C0. So this thing is really a C0. And now we can see, so basically we got like three quantum particles, and we act to C0, we act with a C0 on it, we act with a C0 on it, and we can now see whether we can maybe simplify this or compute what actually happens. We can now start doing this using spiders. Okay, so we saw that spiders fuse together. You see here you got the red spider, there you got the red spider, they're going to fuse together. Here we got three green spiders, they're going to fuse together. Poof. So that was one step of the computation. Now we see a red spider and a green spider, two legs in between. They go away. Oh, now we see a spider with two legs, but that's the same as a wire, because that's just a wire. So we can basically forget about that one. Boom. So what we saw is this was a computation. We computed something here using spiders, and we computed that this thing is really a very complicated way of saying this thing. I mean, it's a very simple one, but that's really what we just have been doing. Right? So, okay. I'm going to stop here. I'm not going to explain you anything more because there is a camera there. And we don't want to give away what I would be saying. Why don't I want to give this away? Because we are doing experiments. We are doing the following experiment. We are going to teach a bunch of young, enthusiastic young adults with this book, the new book. And we're going to give them an exam. We're going to give them an exam, like exercises that they have to do after studying the book, getting some classes. That's why we do the videos. So the videos are intended as lectures, and they will get some tutoring too. And then we're going to take the students from a colleague of mine, which many people in the audience know, Jonathan Barrett, teaches a quantum computing course in Oxford. And we're going to take his students after they took his course, and we're going to give them the same questions. And we're going to then see who does better. Poor John. Anyway, so that's ongoing now. So IBM is helping us with that because they have a large network of young enthusiasts in quantum stuff who are very willingly to participate in that. But obviously, we don't want John's student to cheat and watch this stuff. So that's why we can't have it out there. They only take John's scores. They should only use John's scores. Okay, now I know there's the room here full of professionals, and so I showed a very simple example. But so there is something called quantum non-locality, which is considered as the most mysterious part of quantum mechanics, and it's something where people are already discussing about for 60, 70 years, and they will probably do it for another couple of 100 years. And so what you see here, this picture is basically part of a proof that quantum is what's called non-local, that there seem to be some weird stuff going on between things that are far away and should actually not have anything to do with each other. That's basically things which are far away and should not have anything to do with each other. You can basically show that in case of quantum, they actually have something in connection with each other. And I'm not going to explain how this is, but this is sort of something you can compute in quantum mechanics, in quantum theory. This is a scenario you can compute in quantum theory. For the specialist, this top thing is like a parity check. This is a parity check, and these are your 4 Mermini scenarios. And you can then easily see, using the graphical calculus, the quantum pictures, that this thing immediately reduces to this thing, and so on. And now all we've got is like a few red spiders. We fuse them together. You see they have numbers on them, the red spiders. Basically, if you go to the garden, you see that spiders carry decorations. And then, like with all genetical interactions, if these spiders fuse together, then the decorations add up. They just add up. So you see these things add up, and we get this one. So that's sort of a more extended version of a spider fusion. I didn't explain that. So this is actually what you compute if you look at quantum, and this is what you compute if you look at classical. So basically, some people, it's not important that you know what this is, but for those people who know, these are your hidden variables. Then you see green dots here and red dots. Green spiders, red spiders, and there are 2 wires between each of them, so they fall off. So you end up with a red spider without the decoration. So whatever in our ordinary world can be explained of this scenario, which gives you a spider without a decoration, and in quantum gives you a spider with a decoration. So that's how you prove that in some way the quantum world is not like our world. So the only reason I explain this is to show that you can do complicated things with that stuff, with these simple pictures. Now, why do I say everything here? So these are 3 former PhD students of mine, and what they have shown is that every equation you can derive in the language of von Neumann, the quantum language of von Neumann from 1932, you can also derive with these pictures. Everything. That's a very hard result. That was a very hard result to prove. But you can prove every equation which you can derive in the language of von Neumann with these pictures. That's a very recent result from 2018. And okay, so you can prove a lot with them. Is it useful? Well, these are today all the companies in the world who use these pictures for something. These are all the companies I know of who are now using this. I mean, if I would have showed you this table a year ago, it would be much smaller, much smaller. But today, this is sort of all the ones who are in one way or another using these pictures for quantum, for the case of quantum. So it clearly means that they are useful for something. Otherwise, they wouldn't be using it because a lot of them are big companies. Anyway, so that was one part of the story. Now we're going to go back to 2005. We're going to go back to 2005. Check a little bit on time. Yeah. Right. I was not far down the road here, just a little bit down the road, in Montreal, in McGill. And I was explaining quantum teleportation. This was in the mathematics department there. In the introduction, the word category theory was mentioned. There was a big category theory group. So category theories was introduced as the abstract mathematics of abstract mathematics. So if you want to start reasoning about abstract mathematics, then the thing to reason about, that's category theory. So it's like abstraction over abstraction. Anyway, so there was a big category theory group, and I was explaining this quantum teleportation, and there was somebody in the room. There was somebody in the room who's a very important scientist, a very important category theoretician, and also a very important linguist. He was a linguist. He was a contemporary or either a predecessor of Chomsky, many people may know. And so he came up with theories of grammar in the 50s. This is Jim Lambeck. Wayne, didn't he teach you philosophy or something? Yeah. Yeah. So Jim Lambeck was there, and he said, when I showed him quantum teleportation, he said, Bob, this is grammar. I said, no, Jim, this is teleportation. No, Bob, this is grammar. Oh, he's getting old. Oh, he's getting old. He was right. He was right. He was right. I mean, I didn't know anything about this grammar maths, but he was right. It turns out this grammar maths is exactly the same. Sort of the structure, it's like exactly the same kind of mathematics. It's exactly the same. I mean, at the time I didn't care, but then 3 years later, you see, stuff happens. You don't predict these things. It's not like I'm going to work many years to do this, or no, it just stuff happens. That's just how the world is. Stuff happens. So I had a bunch of colleagues at Oxford. Turns out one of them actually knew this grammar mathematics, because this is Marnusha Zadeh, she's Iranian, and Lambeck had asked her, Jim Lambeck had asked her to work out this new theory of grammar in Persian. So therefore, she kind of knew how these things work. It's like bits of algebra like that. Don't care about what's next to it. I had another colleague at Oxford, and this is Steve Clark, and he knew about what people are now doing in AI. So people in AI, they use mathematics, which is very similar to von Neumann's quantum language. They use things which are very close to von Neumann's quantum language. Professionals call these vector spaces. And they use this to represent meanings of words. Like so you got a dictionary. So for a computer, a dictionary like we use it or used to use it is not practical. A computer needs different representations of what a word means. And it turns out that the sort of von Neumann mathematics is quite useful for that. And that's what's used now in all of the AI. If you hear about all these big AI, natural language models like GPT-3, they all use this stuff. At the time, this was still purely academic. That time, like 2008, this was 2008, this was still purely academic. But he knew about that stuff. And then she knew about this grammar algebra. And then a problem which people had, an academic problem which people had, and which Steve explained us was that nobody knew how to combine these two. Nobody knew how to combine these two. So we know how to do that. We as humans, we know how to do that. If I tell you a sentence which you never heard before, and you know the meaning of the word, you will understand the meaning of the sentence if the sentence is grammatically correct, right? I'm sure that several sentences I just said in the last half hour or so, you never heard before. But still, I hope you understood what they mean. And so we needed to figure out how to do that. So people were trying to figure out how to do that, how to use the theory of grammar, like of putting words together in the right way. Grammar is putting words together in the right way. Putting words together in a way that actually they make sense together. That's grammar. And here we've got this new way of representing the meanings of words. How can we put these things together in order to make something new that we can actually use in any practical way? So that was the question. And I mean, I'm going back now. That was the answer. That was the answer. Because these pictures, the lines represent grammar. That's what Jim saw at the time. These lines are exactly the same as grammar. They form exactly the same structure. And in these lines, using von Neumann's language for mathematics, live this way, these people in machine learning are now representing the meanings. So these pictures, the particles in these pictures are actually the meanings of language. And the wiring is the grammar of language. And that's how you put the two together. So it wasn't difficult. It wasn't difficult. I mean, it was difficult for me because I actually had to learn this grammar theory, which I didn't. I mean, I made this observation. Okay, we know how to do it. But, yeah, what is the grammar theory again? So I need to figure out. And then Steve had to learn category theory. So it was a bit difficult. So we wrote this paper together, which was then, yes, the theory on how to combine meaning and grammatical structure into one whole. So how do you put words together and then produce the meaning of a sentence in a reasonable way? I'm gonna try to explain you how it looks. So the way you have to think, okay, so this is basically just, you remember my 3 lines with then 3 boxes, which was supposed to be like what happens in a quantum computer. So this is supposed to be what's happening in our head. This is happening in our head. This is something that's happening in our head. So we got the word Alice, we got the word 8, we got the word Bob, and those are the words, somebody says. And then these wires, they are supposed to represent how these words come together to form the meaning of a sentence. That's what these wires are supposed to represent, how these words come together to form the meaning of a sentence. So on top, you got what you find in a dictionary or what the machine learning people write down using von Neumann's language for quantum, really. And the bottom, you got what is grammar. So what Jim Blombeck saw is that, yeah, and you see there is a little bit the same as teleportation here going on. You see, you got whoop, whoop, whoop. It's a little bit like this teleportation picture. You see, almost two of them fused together. So that's how this worked. And then using techniques and things like that from the language, von Neumann's language of mathematics, you can then start seeing whether Alice hates Bob really means the same as Alice does not like Bob. That's the sort of things you can do. And so you can do practical things with that. And so that all sounded promising. And then we got a lot of media attention. But people start to call us quantum linguists. And we say, no, this has nothing to do with quantum. This has nothing to do with quantum. This is really a question of normal linguistics, like you know, theory of language. You know how to describe the meaning of words. You know what grammar is, and you just put them together. There's no quantum in there. We said no quantum because I don't know, but at the time, if you say you do language and quantum, then people said you're like a quack, crackpot or something like that. And we didn't want to be called crackpots. So that's what happened at the time. Okay. Okay, fast backward. So this is another Nobel Prize winner, Richard Feynman. And so I didn't have him in my initial pictures, but he said something a long time ago. He said, if you got a quantum particle of quantum systems, and you want to compute things about them, you know, examples of quantum particles are chemicals, all kinds of chemicals. The chemicals in your medication, the chemicals you may want to use to do carbon capture and make the world green, or the chemicals are used in a lot of ways. So, and chemicals are just quantum systems. They're quantum particles, a bunch of quantum particles together. And if you want to understand things about that and do the computations, it's very hard to do this on any computer you've got at home. It's just very hard. It's too hard. It's impossible for most of them. And it says, however, because they're quantum, if you would have a machine that's actually quantum itself, then it would be easy. And that's basically what a quantum computer is. It's a machine which itself quantum, so you can easily compute about quantum things. And he said this already a long time ago, I think a bit over 40 years ago. And however we may have complained that we were not solving a quantum problem, we were using a quantum language to do it. So unfortunately, whatever he was saying also applied to us. We started to use our theory and we were struggling because the computers which people have on their labs here, they're not good enough. They were not good enough to study our theory of language. We're not good enough to do computations in our theory of language. We could, but it was very, very difficult. Okay. I mean, it was 2008. There were no quantum computers. They didn't exist. Okay. So you wait a while, I don't know, you play some rock and roll or you do whatever with your life, and then suddenly the quantum computers are here. Suddenly quantum computers are here. So now we can use the quantum computers to do computation and use our theory of language. So we proposed how to do that, me and Will Zhang. Will Zhang was a PhD student of mine, is now the head of quantum at Goldman Sachs. So Goldman Sachs have like a big quantum division to study finance using quantum. And then there we were still thinking about like idealistic quantum computers. And then a bit recently, I mean, I'm going to go real up. Okay, we did it. We actually started to do the sort of thing I showed, like combining meanings of words into the meaning of sentences and then do interesting things with that. We started to do this on actual quantum computers. We did this for the first time in 2020. And then we did it a lot bigger. So this, just to give you an example, we use like a couple of hundreds of sentences here and then try to study them and do some question answering and learn things from these sentences. So that's what we were doing there. And now you can do it too. You can do it too because we actually, all the sort of stuff we produced to talk to the quantum computer, to play with the quantum computer and to do all the sentences things, we basically made quite easily usable for anybody, and we just gave it to everybody for free. So now everybody can do this, and there's now a big community. We've got like a Discord site where lots of hundreds and hundreds of people are sort of playing around with this, playing with sentences and words on quantum computers and trying to learn things from it. So this is real. This is real. This is now happening. This has happened. This has happened. This is real, and you can actually go home today and do it yourself on an actual quantum computer. On an actual quantum computer, because many quantum computers by IBM, you can just access. You can just access, and you can just do this yourself now. Okay. So that's, so and then, so we released the first version a while back. We now, in 2021, now recently we released a new version. So we keep on making this better and better and more interesting and more interesting. And yes, okay, so that's going on. Like now, how do you do that? How do you do that? What are we actually doing in there? So what's happening? I mean, there's a lot of complicated stuff happening, like talking to the quantum computer, which I'm not going to explain. Like with anything, for anybody who knows software, there's like a compiler, there's all these different things are in there. So it's very complicated. But essentially, the core is just, again, just transforming some pictures. So you remember, this is the picture which happens in our head, when we hear a sentence and the way we actually put these words together to give the meaning to the sentence. That's what's happening in our head. So that's the picture. So okay, now we want to give this to a quantum computer. You remember, okay, I'm going to go a very long time back. This is the sort of thing you want to give to a quantum computer. So you got your quantum particles, and then you got your boxes acting on it. Now we want to take our sentence and we want to turn it into something like this. So let me show you how to do that. Right. Oop. It's going to go in a few steps. So I've got this one. Up. So, you know, I've got, what I'm going to do first is I'm just going to pull out some, I'm going to think that inside here there are some spiders. See, I'm going to assume that there are some spiders living in this box. Boom. Okay, there's 2 spiders in the box now, and this one is a little bit smaller. There's 2 wires now. And then I'm going to pull these spiders out. You see? I'm pulling them out of the box. I'm pulling them out of the box. Now here I've got a piece of wire. Here I've got a piece of wire. There I've got a piece of wire. I'm pulling out spiders. See? I can always do that because the spiders fuse together to a wire. So they fuse together to a wire. Now I pull out the spider. Pulling out the spider is the opposite of fusing them together. It's the other way around. And now you see what's here is what I told you earlier. Like if you, the colors change, now it's white and gray, but so this would be green and red. What's here is a box you find inside a quantum computer now. This is a box you find inside a quantum computer. And then you can just do funny things like you remember, like pulling boxes upside down. This is not really necessary, but just makes it a bit smaller. And now you remember at some point I said, I had this slide with everything. You can write everything down, which you've got in the language of quantum mechanics using spiders. So we can do this here too. We can do this here too. We fill all the boxes with spiders. This game went very quick, but this is really, so this is the sentence which I started with, how it looks inside a quantum computer. And it's just made up of spiders, just made up of spiders. So now we're back to the beginning of this talk. We went from the language to the spiders. And this is the thing which goes inside a quantum computer. Right. Okay. Now, so far, we were using the theory of language, which Lambe came up with in the 50s, and which is very similar to what Chomsky did and all that. So this was a theory of language, which goes back to the previous century. There's nothing new about it, nothing new. We just used it in a different way by using this language of quantum and these quantum pictures to put it together with the meanings of words from machine learning and things like that. But it's interesting that you can actually change language. So you see, all these words live on a line. They all live on a line. When I speak, I say one word after another. Say one word, then the second word, then the third word. If I would say 10 words at the same time, you wouldn't understand what I'm saying, right? It would be really difficult. So I can only really say one word at a time, and you can really only hear one word at a time. That's just the way we speak. That's just the way it works. That's our limitations, I think. That's just our physical limitations. It's kind of interesting that you see this, and now there's nothing about the line anymore here. It's like a completely different thing. It's like a painting. It's a painting. It's like, rather than what people call one-dimensional, a line, this is a two-dimensional thing. And I recently became convinced that language is fundamentally two-dimensional. Language is not things one after another on a line. Language is something you want to draw in a plane. And that's a new theory of language. That's an entirely new thing, very recently, which we came up with, and I want to explain now. So we've been talking so far about a new language for physics, a way to using this new language for physics to combine grammar and meaning of words. Now I'm going to go to a new theory of language, which is very recent. So we haven't done very much with it, but I'm going to show you something which I find incredibly compelling. And that'll be more or less the last thing I'll be saying. So this started in this paper, The Mathematics of Text Structure. So my first initial concern was all these theories of grammar. They tell you when you put words together, when they are correctly put together to form a correct sentence. So then we sort of turned this into a way of combining words to actually, and the meanings of words to produce the meaning of a sentence. You combine words in the diagrams and they produce the meaning of a sentence. So what about the meaning of a text? What about the meaning of a book? I think there is one book which is one sentence, but most books contain more than one sentence. So you need to find a way to combine these sentences and the meanings into text. And with what I've been presenting to you, it just didn't work. It didn't work. Well, it did work with the last bit, where I was actually turning everything in circuits. Let me show how this works. So I've got a sentence like this. Alice hates Bob, and now I write it a little bit differently. Yeah? The way you have to think about is like, you got Alice here and you got Bob, and now then hate sort of brings them together. in not the best possible way, but it brings them together. Like, I think of this as these two white spiders as H grabs the two. H grabs Alice and H grabs Bob and brings them together. And now I can continue. I can continue. Like Alice hates Bob, and then yeah, Bob gets put together with beer by liking. And you see, and I can go on. I can go on as long as I want. I can go on as long as I want. So this is a way to actually put multiple sentences together. And it's kind of, okay, just to give you a visual representation of what's happening here. What's happening here really is, so this is a much more complicated thing. I don't know, I mean, there's a lot of Italians here, I think, in the audience. So I don't know whether they recognize this. You will soon. What is it? You don't know? Okay, you will soon. So this is really a representation of language. This is a representation of a few sentences. Harmonica is the brother of Claudio. Frank hangs Claudio. Snake is in the gang of Frank. What is that? What is here? Harmonica shoots Snakey. Harmonica shoots Frank. You know? But you see how I'm reading this? You see how I'm reading this? Huh? So I'm just reading this as if this is a book, a piece of text. I read this as a piece of text. And of course, I can represent this differently like this. It's the same story. So the way these circuits are much more like we watch a movie or we perceive like a story when we visualize it. Rather than like word by word, like you find it in a book, this is sort of more a visual representation of what happens, a storyboard in a movie. So it sort of starts to tell you, it's kind of a little bit closer to how we think, probably. It's probably closer to how we think. But these were all intuitions. These were all intuitions. So then, me recently with two students, we went to do the hard work, and we said, we're going to do this for all of English. We're going to turn all of English into such pictures, which are not just, where the words are not just on a line, but they are sort of displayed as a painting, really. And I'm going to show you with an animation. So don't try to understand this, but because this is complicated grammar structure. So this is really like, for people who have ever heard about Chomsky had these three structures, these things which look like this to represent grammar. That was a sort of Chomsky stuff. And so all this stuff which is going on here are bits of grammar theory. And this looks really complicated, right? This looks really complicated. We've got a sentence here, sober Alice who sees drunk Bob clumsily dance, laughs at him. And so we came up with an algorithm for all of English, not just for this sentence, which gradually starts to do things. You see, I mean, this is really art, come on. See, we start to gradually deform that. We're just deforming the thing. That's really what we're doing. And we deform it a bit more. And then we start to turn some of these words into boxes. And we turn some of these words into boxes, bang. So I believe that this is much more fundamental, much more deeper what language is about than the words all on the line. I believe it, and I'm going to prove it to you. So let's read this. Sober Alice sees drunk Bob dance clumsily, laughs at him. So it's all that stuff, all the information is there. All the information is there, just like before I was reading these things. All the information is there. Now I'm going to show you interesting things. So, okay, we did this for all of English. Let's move to French. So this is the same thing for us. I really love you. I really love you. English sentence. This is je t'aime vraiment. So these things are different in French and English. In French, the order of the words is different than the order of the words in English. And this gets much more complicated for long sentences. If you move to these boxes, they become the same. Different languages become the same. We recently worked this out for all of Urdu and English. For all of Urdu and English, the differences in the language all become the same in these boxes. They all become the same. They all sort of, so this sort of proves that this is like really universal language, which underpins all languages and where all languages come together. Here is another example. There are people who like to say things simple. many short sentences. Then there are people who want to show off and they say everything in very long, complicated sentences nobody understands. That's a different kind of people. Someone wants to show off, someone wants to actually explain. So we got here, sober Alice, who sees drunk Bob clumsily, Dems laughed at him. Long sentence, very hard to parse. I can hardly read it. We see Alice sees Bob dance clumsily, Alice laughs at Bob, Bob is drunk, Alice is sober. And then we got the same in French, where the words are a little bit mixed up. They all become the same. So the difference between this style just vanishes when you go there. So this is really sort of the language which we should be speaking. We should be speaking like that, and we should be listening like that. This is the way to communicate because it's much more pure. There's no language differences anymore. There's no style differences. But we can't do it. But computers can do it. Computers can do it. So let me show. So we came there from, okay, oh yeah, this doesn't work. We're just going to go a little bit back. We came there from trying to put a sentence, where was it? Trying to put a sentence on a quantum computer. We started to think, hey, that's an interesting form of language. So we took this seriously. Boom, 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 boom. And we end up with something that has everything you need to know about something you want to say, but the words are not written one after the other anymore. They're all sort of with boxes and all like that. But all the different languages become the same. All the different styles of speaking become the same. So it really captures something really fundamental about language. And I mean, we're now trying to stick this on quantum computers, obviously. And also on normal computers, by the way, because it's actually much simpler. Okay, fancy writing, show off vanishes. There we go. Right. So, I mean, obviously, so when we speak, we have to say word by word, word after word. When you read a book, it's just word after word after word. It's just one long line of words. Obviously, we as people, we can think at things at the same time. We can think in these terms, because when we play music, I mean, this is a score of something I wrote, of music I made. You see how many things at the same time are going on. And we can perfectly hear that. We can perfectly sort of perceive that and imagine that. So we are perfectly capable of thinking of many things at the same time. We're perfectly capable of doing that. When you play music, yes, you see, we're three now. This is the band, now we're three. And this person, by the way, was the one who did the first implementation of the natural language on a quantum computer. And this is Alex Kissinger, with whom I wrote the big book. And this is Ross Duncan, who I came up with the theory of red and green spiders. And Matty Hoban is well known in this community. Right, so just to say, when you play music, you really hear all the instruments. If you play music, you hear everything at the same time. So there is the possibility. So it doesn't work with words, but it does work with music. We can perceive things at the same time. So really our brain is made to think. Our brain is really made to think, in these terms. Our brain can think in these terms. It can. We can perceive that. But we just can't communicate it with our mouth. That's all. Okay? So since we're in the theme of music, we basically also wrote a paper with the help of a composer, where we used, you know, the thing which we gave to the world for doing playing with language on a quantum computer is called Lambic, for the obvious reason, because it was Lambic who screamed out, this is grammar. So we called this Lambic. So we actually used Lambic and changed it a little bit, we tweaked it a little bit, and we turned it into Quanthoven. Quanthoven, because the sort of grammar, the structure of language can also be used to structure music. People have been doing, composers have been doing this for for very long. They just use same kind of maths to compose music. So we adjusted our Lambic a little bit and turned it into Quanthoven. And we made some stuff on the quantum computer. And we ended up #1 in the classical charts. Bob Cigarbus. Ludovico Quanthoven. Quantum computer music. Anyway, let me check the time. Yeah, since this is a meeting about, the meeting here is about space-time, let me just make one final remark. Basically, you can also think of space-time in exactly the same ways as I've just been explaining. For music, for language, for quantum, of course, you can turn space-time in exactly the same sort of format. Basically, space-time, language is very, there's a lot of space-time in language, a lot. For example, when we use prepositions like in, next to, after, on, with, these are all spatial connotations, all of them. They're about space. Many word meanings like chasing and all that, many important words, they all have spatial connotations. When we talk, we point. We make reference. I've been pointing the whole day here, the whole talk. We point. Where do we point? We point in space. And that's an important part of communication. And in fact, it's where we exist. I'm moving around here. I'm moving around in space. We're all moving around in space. I mean, I think it's, and I'm not the first one to make the claim, it's fair to say that space-time is actually the origin of language. That's where it started. When like a bunch of our forefathers tried to take down like a big mammoth, they needed to coordinate, they needed to communicate in some way. And so you can imagine that language just arose from like these spatial coordination exercises. So let's do the other way around. Let's go the other way around. Let's now use language to capture space-time. Can we use language to actually represent space-time? So we did this in this paper, very recent, me and Vincent. And basically each Y, like a space, like, okay, this is my space. This is my space now. Here I'm moving around. You've got your space. You've got your space. Each of you has your space where you're sort of moving around in. We each have, sometimes we bump into each other, but we all have this space in which we can move around. So each wire is a space now. And each box is a way that we are related in space. Like we are like 5 meters apart. That's a relation. We're 5 meters apart. We are like 15 meters apart. So that's a relation. That's a box. A box tells how we are related in space. And then you can do things like this. So basically, this is like our language theory from before, or language diagrams from before. And basically, this sentence is giving you exactly the information as this spatial figure. It tells you that the pawn is next to a king. Pawn is next to a king. Knight can capture that pawn. Knight, where is the knight? I don't see the knight. Can you? Oh yeah, knight can capture that pawn. So and it turns out that happens to be sufficient information to characterize this pawn. But so this sentence is like a way we can represent this in traditional language. In traditional language, on one line, when you put it on two lines, like in 2 dimensions, it's much easier. So it's just the pawn next to the knight, which the knight can capture. It's much easier. This is much easier. So this is a much easier way. So the new language which I propose, of course, much easier for this. And you can do the same thing, like this is another example, more complicated. The ostrich next to a tree that a cheetah next to grass can capture. This is again like a linguistic representation of this spatial feature, which then again can be represented in a much more simple way. The grass next to the cheetah, ostrich next to the tree, cheetah can capture ostrich. So you start to see how this works, how you can actually convey meaning with this diagram, with these sort of 2-dimensional shapes. It has all the information you need in a much more simple way, than this. This is something we need to do in our head when you hear that sentence. This is something we need. All this wiring is something we do. We do that. We have to do that to understand what is being said here. This is what all the work we have to do, because we need to hear word after word after word after word after word. So yeah, I mean, and then you can basically unfold this much simpler into this. Anyway, so how times have changed. When we wrote this paper in 2007, Ross Duncan and me, about the theory of red and green spiders, this is what our colleagues said. Where does this lead us? Important results do not occur in the present paper. It wasn't good. It wasn't good. This is where it leads us today. This is where it's being used. Now, and next year, this will be just packed and packed and packed and packed. No, believe me. And then, okay, so category theory. Whenever we had in that time, because the reason these people said this is never going to lead to anything is because people said category theory is never going to lead to anything because it's abstract maths over abstract maths. We would like you to give we would like to invite you to give a public lecture at a conference. Category theory would be a very interesting topic for it. So from useless for scientists, it became interesting to the public in like some 15 years. So that's a good place to end, I think. Thank you. By the way, everything I've been talking about is category theory.
I see two questions in the public, but I think that I will shamelessly start myself with some questions and comments, because so you're connecting language with the physics of quantum system and the physics of space-time. And I have been wondering during all your talk about how do you think about the relation between language and the physical world.
Language
and the physical world and the physical reality around us. So I wonder, there are two possibilities. One possibility is that the quantum systems, the physical quantum systems that we study, they are nothing but language. But then in this sense, are they just our representations, internal conscious representation of the physical world? Is that is that the properties that we attribute to the quantum system, or even the property that we attribute to space-times, are such just because this is the wire of our brain? I mean, language is in the end really the wire of the way we think. So what is the relation in between the two?
Okay.
So this is my question, and I just make a small comment. My personal take is that certainly consciousness, so language and consciousness are related, but consciousness is related to the development of neural, of motion in biological systems.
Mm-hmm.
So it's quite natural, this final relation you are making with space-time between the spatial the understanding of the spatial relations. And if I can just add a small thing regarding the development of language in human beings, I wouldn't use the hunting picture, because there is the idea also that the social relations, not just for hunting or war, but for motherhood and social relations and gossip may be at the core of it. So
now I have to sort of go back. First thing, I think, how is language related to let's say the physical world? I mean, I made the claim. I think language is just a representation of how we interact in the physical world. That's the structure of language. Unfortunately, due to the limitation of our vocal organ, we have to turn this representation of the physical world, which for me, this representation of the physical world is this. We have to take this representation of the physical world and turn this into something that lives on the line. So we actually, what we do is, this is what the world out there, this is how we understand the world out there. These are just hunting processes, that's probably where we stand. And then we have to change it into this, because that's the only way we can sort of communicate. So the thing is, like, to do that, you have to make a lot of choices. There is a lot of choices involved. And that's why different languages are different, because the French made different choices as the English, obviously, they always do, and so on. And that's why this is so complicated and so full of bureaucracy. So I don't think that you have to go quantum at all for that. You don't have to go quantum at all. This is really about this sort of relational structure. These are relational structures. It's really about these relational structures. However, I think the other way around is what we actually, in a way, I work backward, because what we did is like we think about the world in this, and then we start looking at quantum. And then we turn quantum language into pictures, just like these pictures. And then we learn something new about quantum language. That's really how it should have happened, but it kind of happened the other way around. But that's what I think it is. Like we actually start to think about a physical quantum in these terms, and then you learn something entirely new. Then we ended up like discovering this red and green spider. This red and green spider is very specifically quantum. It's actually very specifically qubit, so to say. Well, not really. I'm saying something wrong here. Not really, but it's very specifically quantum. It's not easy to see how they naturally would become part of like the way we speak or anything like that. Although to some extent they did, but only spiders of one color. So the two colors are what physicists call complementarity. And obviously, in the way we speak, we only need one, because that's the world we live in. So you see in all these pictures, we only got spiders of one color, which is totally natural. You see, there's no two colors, there's only one color, which makes perfect sense for people who understand quantum. Then there was the connection. So yeah, I mean, we are now working a lot on extending this model of language to a model of cognition. I wouldn't say consciousness yet, but a model of cognition, like incorporating all or other sensory information we get and try to make them indirect in the same way, because you can actually shape all the sort of cognitive sensory features we have in the same way. And this is our approach. This is our approach to actually, technologically speaking, to a new generation of AI. That's to a new generation of AI. But I also think it's just a new science based on togetherness of everything. Because particle physics, all of science has been completely dominated by breaking things down in small pieces. Well, not too long ago, if you ask a scientist, like, let's figure out stuff about a human, they would take a knife and chop them open and see what's inside, right? That's been the approach for a very long time to everything. Particle physics, chop everything down in pieces and see what's inside. Here, this is for us the new way to think about science, and it's like about how do we interact with others? The child and the mother, you just said it. That's how things are created. And that's sort of the way we think. Like, things are created when you bring things together, and that's how we need to understand the world. I'm not saying that chopping things down in pieces is not useful, but we've done it for long enough now, so now we have to do something else.
Thank you, Bob. Seems to me that it's a nice example on how understanding more the fundamental world, the physical world, we understand also something more about ourselves and the way we.
I think we can learn from ourselves about the physical world. That's really an exercise here. Yeah.
So thanks, Bob. I really enjoyed it. And I have a follow-up question on Francesca's question. And I think you just maybe answered this a couple of minutes ago. These diagrams that you use for language, you said they are in one basis, in a sense. Like they are not complementary bases.
Yes.
Shall I understand this, that these are classical diagrams that I...
Yes.
Or just to finish, or do you have an idea whether you can show that some parts of the language necessarily need quantum diagrams, like your spiders, decorated spiders?
I didn't want to go there because I didn't want to be called a crackpot, but maybe yes. Maybe, although again, it's hard to see what quantum and classical them would mean. It's really that you need the same structures to describe the same thing. I mean, there has been work in cognition that the sort of ideas of complementarity is kind of related to the bias in which people ask questions. Like you can actually ask a question in a different way and people will give a different answer depending on the way you ask it or whatever you said around. And that's kind of a little bit similar to the complementarity idea. I think. So it's not going to probably be exactly the same thing, but there's definitely things you can learn from it. Definitely. But I think the language stuff will be much richer than the quantum stuff. If you do it properly, it will be a much richer and complex structure.
Thank you, Bob. I have a question about, are there linguists using these diagrams to build explanations and predictions, or is still very much within?
I don't hear
this microphone well.
Yeah.
Yeah. Is it this language, these diagrams being used in linguistics to, make predictions about linguistic phenomena or explanations?
I mean, the thing is like, just to give you an example, like you've got a big text and you want to figure out whether what's the sentiment? Is it positive? Is it negative? And then you would use something like this, like sort of, for example, BBC. BBC has like this humongous archive of documents, which is unhumanly possible for anybody to read. So they want to use machines to analyze or classify these things. So these are not just sentences, these are pieces of text. And just to classify them, they think that this sort of theory can actually then be used because you actually have a way to assign meaning to an entire text. You can then figure out what the sentiment is. So in finance, sentiment is really important. So that's why finance is interested in this sort of thing. That's why JP Morgan is interested in our diagrams and is using them, because they think they can use them for sentiment analysis. See what the sentiment of the market is and things like that. So it's very practical. This came purely from this combining words and the grammar came purely from a practical demand, 100%.
So I find amazing the fact that you can more or less map the languages to the same representation in some sense, right? So this was amazing. My question is,
that's the right word. We were shocked because we didn't do it for that reason. We just wanted to make, and then we saw that this magically happened. You can imagine how shocked we were ourselves to see that.
My question is a little bit different. How do you read these diagrams? Is there any there's
no unique way. You can't read them in one way. That's the whole point.
Mm-hmm.
They are two-dimensional fundamentally, and then
so it only makes sense if you take all the information.
If you're gonna want to read them, then you're gonna invent the different languages, reinvent the different languages depending on how you read it.
Yeah.
In the order you want to read it. So yeah. So
there's no ordering in this.
That's the whole point. There is none. There is none.
Okay.
And if you want to order, you have to make a lot of choices.
Mm-hmm.
So you introduce a lot of meaningless bureaucracy. And each language has different meaningless bureaucracy. And it's really interesting that, I don't have it on a slide, but like for different language groups, if you look just at the wiring structures, you can sort of recognize, okay, this is like Hebrew, this is Persian, this is English. For example, in English, the little connections are always very close. In Persian, they fly from one side from long sentences to another. So you can really, and you can also see that, for example, Hebrew is actually quite similar to Arab. You can see these things just from the wiring structures. I don't know why people made these specific choices. I don't know why. Yeah.
Hey, Bob. So you mentioned how the vector model of meaning that's used in linguistics, it has this natural counterpart to the vector space that's Hilbert space in quantum theory. But I can also formulate quantum theory, at the level of operators, so instead of the category F-Hilb, you do the CP construction, and that's also a vector space. It's now the vector space of real Hermitian operators, but I still have a tensor product. I still have cups and caps, and I can do it all the same way. But once I'm in that vector space, any generalized probabilistic theory can be expressed in that language. And in particular, classical probability theory can. And the cups now are maximally correlated states rather than entangled states and so on. And so it seems to me, I guess my question is there anything sort of about the kind of vector space of Hilbert spaces that's closer to the vector model of meaning than, say, the vector space in which I could describe classical probability theory? And then the final question is, do you really need a quantum computer, or could you use a classical probabilistic computer to do a more natural simulation of some of these models?
So I'm going to answer two things. First, on classical similability. So now I have to go technical. I know I can only answer this in a very technical way. So these circuits, we looked at some texts, are highly entangled. They're highly entangled, and and given the way the meanings are built in natural language processing, they're highly non-Clifford.
They're highly what?
Highly non-Clifford. They're totally non-Clifford because the whole space is very densely filled, especially in the modern language models, which are like very condensed. So no way you can classically simulate them. There's no way you can classically simulate. Now, your first part about like going to density matrices, that's a very interesting thing, because why did von Neumann invent density matrices? To express ambiguity about a quantum state. Now, one thing in linguistics which is super important than in natural language processing is dealing with ambiguity. Because language is so ambiguous and much more than we know. And now to go a little bit philosophical, like I have the word compositionality there. Compositionality means how you build big things from small things, like how you build a sentence from words. That's what it meant. And there is a definition by Frege, which defines compositionality like the fact that you can get the meaning of the whole from the meaning and the parts, and how the parts are stuck together. So that actually doesn't work anymore. Modern machine learning doesn't do this anymore. A lot of the meaning goes top down rather than bottom up, because the context actually resolves the ambiguities which you find at the bottom. So actually what I do in this paper is come up with a new definition of compositionality. And also quantum doesn't have the traditional bottom-up definition of compositionality, because you can't reduce a Bell state to its parts and the way they're put together. You basically need the state itself to describe it. So yeah, there's a lot to be said, but this is really the edge of where things are happening now. But you need a quantum computer because of this highly entangled and non-Clifford, so very hard.
Oh, hello.
But there are people who need to speak, so sure.
Yeah, an example of the top-down aspect of meaning is your use of can capture in both of your examples. The sense in which a knight can capture. That's totally different from the sense in which
the top-down. It's more complicated than that. It means that this is a very well noted. I didn't want to say this, but you have to actually change the space in which you work, because the space is not just the space in which you live and act. It's also your capabilities with respect to this space. Like, for example, the examples I had with the cheetah and the ostrich, the endurance of the cheetah, the speed of the cheetah, the endurance of the ostrich, and the speed of the ostrich is part of the description of the space. So your space includes a description of your own capabilities. In this case, chess pieces, whatever move they can make, it's part of their description of their space. So what you suggest is that you stick it all in can capture, but that would be too much. You don't want like all the chess piece information, all the information of all the nature in that word. So you better stick it in the space. So but indeed, there was something we actually had to think about.
I am unfortunately in the very unpleasant position to have to keep the time and have to close the session, even though, of course, there were several, I can count at least some 10 questions from the public, so maybe the questions can be taken later to you, Bob, but I need at this point really to pass a great applause to Bob for his presentation.
Thank you.
Thank you so much.